Okay, so what we'll do is I just want to make sure that we are aware of some things that are online on the Cal Poly portal here, on your Canvas portal. I'm sorry. So on your Canvas page now, there is this this next set of lectures on traffic engineering studies applications. So we'll start that on Thursday, and then I have the problem set 1 posted, and you're supposed to just sort of, these are essentially 6 problems, I think there. And on those 6 problems, some of them are sort of relatively simple. And, so there are 6 problems total. You will be able to solve about 3 or 4 of them right now. And then I think once we end the lecture today, so I think there are only 6 problems actually. So I don't know why this 7 and 8 shows up here, but I'll take care of it. But there are only 6 problems on the homework set. And this is due on the 13th. So this is due in a week from today, right? So that's what I said here. Let's see. This should be due. This is due on October 12th. So a little bit over a week from today. And the problems are always due on midnight, these problem sets. But we'll have, I think by the time we end the lecture on Thursday, you should have all the material that you need to solve all the problems. So it might not be a bad idea to sort of get rolling on these, at least get started a little bit and see where you're getting hung up on. And then, stopping by during office hours, either tomorrow or, after Thursday. We can also sort of talk about any of these problems in the class. So if you have any burning questions that I think might be of interest to the whole class, we can maybe spend a few minutes on Thursday in class as well. I think those are some of the important things that you need to worry about, because a lot of these concepts are great to learn, but then again, when you apply them in the context of a problem, that's when you realize what you're missing out on. So these practices are great. And some of these problems are very similar to what you might see in your PE licensing exam, in the afternoon exam, if you were to do transportation, which I think nowadays, transportation is probably the best bet to take, especially if you're a transportation person. In the past, I know a lot of transportation people would take geotech exam or water resource exam because they didn't want to take all the manuals, but now there are no manuals. It's a computer-based test. Yes.
Effective 2024, the PE civil exam changes. So the PE transportation exam has no more structural, geotech, or water questions.
Oh, so not even the morning portion?
No, they completely changed the exam. So they effectively doubled the amount of transportation question, no more structural, no more geotech, besides what a DCP test is, and no more water except drainage.
Oh, interesting. So I was not aware of this change. This is a great,
Effective April 2020.
So April 2024, what I've been told just now is that the format is changing to include more of transportation, which I think would make it even easier. But what used to happen in the past, like when this was not a computer-based test, I know a lot of, and senior design advisor, Professor Paul Valadeo, I know a couple of other people who are transportation people, do transportation as practice, but they ended up taking geotech exam just because they didn't want to take all the manuals that were required to be, part of the test taking thing. So, but now obviously computer-based test, now it's not even, you're telling me that there is not even a lot. So I would love to actually learn more. So this is kind of interesting to me, fairly useful stuff. So something that, yeah. So your problem set does include a lot of problems that are going to show up, similar problems in your licensing exam. So might be something you want to pay attention to. And then the other reason is that the test is going to look pretty similar as well. So there is going to be some conceptual question in the test, but the problem set would look pretty similar to what you're seeing in the homework problem. So you might want to just get rolling on those. And then let's see. And it does require you to maybe potentially make some assumptions, kind of think about certain questions critically. So this is not, so it's okay that, some of these questions you might end up with different assumptions, maybe even a little bit different answers, and that's perfectly reasonable. And as I've said before, it's okay to talk to each other about these homework problems. What is not acceptable is that, you just sort of copying somebody else's solution. If you want to talk to somebody, your classmates, that's perfectly fine for the homework problems. So always feel free to do that. Okay, so what I'm going to do next is I'm going to go ahead and pick up where we left off last time. Oh, and one more thing I need to do is I just want to pass out these handouts. These are not going to be useful today, but these are going to be useful in the next class session. But I want you to sort of maybe give it a quick read. Pass one, take one, pass the rest along, please. So yeah, I want you to give it a quick read. Not today, but maybe at home. And then on Thursday in the class, we'll try to work out some example problem that deals directly with this. So make sure that you bring it in the class on Thursday, and then give it a quick read if you can before the class on Thursday. That'll give you some orientation about what this is about. This is about thinking about traffic signal warrants, and you might have seen some of these if you've been an intern. This is sort of a common thing, but we'll talk about some of these details. And these are federal warrants, and sort of bad news is that these are about to change, but they haven't changed yet. So within a next, I think any time now, they could go into effect. The new warrants could go into effect. They've been passed, they've been vetted, but they're just not out yet in the public. So we can't quite use them. But that's fine. I think the most important thing is to be able to make sense of what's here. Like maybe not. So even if the precise warrant that you're going to apply in practice in the future, or if you're going to look at the California MUTCD, those warrants are pretty similar and require sort of similar type of comprehension skills that you will require to look at these. So it's pretty similar, even though they're not going to be probably the same that you're going to apply. All right. So what we'll do is we go back to the traffic engineering studies. Yes, please. Do you have any more copies? Yeah, I do actually. I don't know why. Okay, so yeah, copies. Whoever looking at it, just take one and pass the rest along. And again, these are also posted online. So if you go back to your sort of Canvas page here, so if you go back to your first module Canvas page, you can find it here as well. And the one thing I want to point out again is that if you ever want to sort of catch up, or like if you miss a class, or if you want to catch up on some things, then the videos are posted here. So if you click on this link, that takes you to that playlist where I'm recording and providing these videos. And again, they're not a substitute to coming to class. As you will see, the quality is fairly poor, a lot of pauses. Sometimes I'll repeat the question, sometimes I won't. So again, it won't be a great substitute, but it might have to do the job in case you have to be absent from the class, or you want to really go back and sort of look at a certain concept that you might have missed in the class. So it's always possible to do that. But again, I would appreciate your engagement in the class anyway. Okay, so let's see where we were. Talking about these. So these are sort of mechanical boards. So these are sort of electronic count boards that are now used. So they're just, pretty easy to use. So anytime there is a left turning vehicle, they have sort of the turning movement assigned to them, and you could see what these movements look like. So anytime there is a vehicle sort of making a turn from there, you just sort of pass that. And then, anytime there is, so this is sort of the turning movements that might be assessed. And then, so yeah, and then the good thing about these is that once you collect all the data that goes into electronic format, it gets automatically assigned as a sheet. And then the sheet might look something like this. And one thing I want to quickly show you is that, and then this is something that you will use in the lab as well. So if you go to Slow City traffic data, not the street light data, this Google search, I was reading an article, they are always looking to sort of monetize these things. So they always put what I've heard is that they even change these queries that I'm putting in. The algorithm or the computer systems where they generate the search results doesn't actually see what I'm entering. It sees something altered, which is sort of generates these sponsored results more often. So there is a lawsuit going on. I was reading about it, pretty fascinating. But anyway, so traffic data, if I click on this, I can go onto the link, And this is something you might be seeing, or you might have already seen in your lab as well. But you can click on any of these intersections and you can see what type of control it has, and then you can zoom to it. And then once you click on more info, you can actually see the output data from some of these traffic counters. And some of these traffic counters might actually be the automatic traffic counters. They might not be manual at all, but you can see all that data, and then you can see this broken down by through, right lane, and all of that. And then this sort of indicates the number of lanes here, how many number of lanes are there. And if the movement is not just there at all, then it's just X in there. And so that's why you see only no westbound movement. This might be a T intersection. So, or T intersection, or just kind of a one-way street, which is Higuera and Marsh intersection is. And then you could see the pedestrian data, all of that is in there as well. So yeah, all of these data sort of gets into it and then gets filled up into these cells. And these sheets can be automatically generated once you connect that device, the data collector, into a computer. Either you plug it in or Bluetooth or whatever technology we're using. These are the sort of data that comes in, and hopefully get just work with some of that data in the lab. And there is another example that's shown here. You know, electronic boards output, and you could see that here. And again, you know, through, right, left, and then from north, from east, from south, from west. Okay, so sometimes the data is provided like this, but then a lot of times it will be like eastbound, westbound. So you just have to be careful about reading these things. So from west is basically just sort of eastbound, right? And then from east is westbound. So just kind of be careful as you're reading these things, reading these numbers from a sheet, and maybe you're taking a look at these sheets to build a Synchro model or a vSim model or whatever. Just be careful about reading these, because as I was showing you in the slow city data, that's more like northbound, eastbound, southbound, westbound. But in here, it's kind of like from west, from east, from south. So just be careful about this stuff, okay? So something to look at. And I think we did this already. We talked about this quite a bit. So just sort of existing traffic volume. And then this is the phasing diagram I mentioned last time. We won't worry about that yet. We'll worry about that in module 2. So here is the question that we sort of left off. Is what time should we collect the traffic volume? So what do you think? What time should we collect the data, right? Yeah.
Peak hour.
Peak hour, yep. Go ahead. You had a point too? Right, rush hour traffic, but obviously, unless you've collected the data, maybe you've collected the data in the previous years. So you have some indication of when the peak hour happens, but you don't exactly know all the time when the peak hour happens. So you might have to be, cognizant of the fact that, maybe the peak hour is something you don't know. So you might have to collect, like, sort of be a little bit more conservative in your choice of collecting the data. So kind of go out and collect the data for a broader time interval, and hopefully you find the peak hour. So you, instead of collecting the data for just 1 hour, which you may be interested in, the peak hour, but you don't know what that is. So, and this could change from time to time as well, especially now that that COVID is, since COVID, the remote work has come in a little bit, and people are maybe increasingly able to align their work schedule. At least some of the people can align their work schedule with traffic, or when they have to pick up the kids or whatever it is. The peak hours might be a little bit more, shall I say, spread out and not be at the same time that they used to be. So especially since COVID, if you have locations where you haven't collected data since the pandemic, maybe it's a good idea to kind of expand that data collection window a little bit to get a better picture of your peak hour, because peaks might have flattened a little bit in some ways, and they might be more spread out now. So something to think about. What days of the week we typically collect the data? Yeah.
Depends on the location.
Definitely depends on the location. Most locations you could get away with Tuesday, Wednesday, Thursday data collections. But again, those things might be changing now. And and you always have to be worried about when you collect the data, right? So whenever you collected the data, you have to always note that when you collected the data, and then those things might affect the outcome, certain times. So, but your typical goal is to get, so your typical weekday data, and that used to be, at least pre-COVID days, we always used to say, go out and collect the data Tuesday, Wednesday, Thursday, and then do it during morning hours, midday hours, and like late afternoon, like 3 o'clock to 6 o'clock hours, and you'll hopefully find your peak hours for the morning, midday, and afternoon. But those things are a little bit, in the flux now, still are, even though a lot of people, most of the people are back and they're working most of the time in person. There is still some of that traffic patterns have in fact altered for good, and then you have to be aware of those. So this is what sort of like the traffic volume typically looks like. And then if you think of this line as your capacity line, so anytime the demand exceeds capacity is when you have congestion, right? And then the congestion, as you can see, seems to be more persistent during the afternoon peak hours. And this is interesting, right? We used to always say that collect data on Tuesday, Wednesday, Thursdays, even though we knew from practice that the Friday rush hours are the worst ones, right? So if you look at traffic on the street, and if you're driving experience or as a passenger, think about it. Friday peak hours are typically the worst because sometimes they will combine both sort of workday traffic ending and sort of leisure traffic at the beginning, and maybe people are traveling or whatever. Those things could get pretty out of hand in terms of traffic. But we never used to collect the data, partly because we used to say, okay, yeah, maybe the Friday traffic hour is the worst, but maybe we don't want to always design for that, right? So yeah, we want to identify the worst hour, but maybe not the absolute worst hour of the year or of the week or whatever. And we'll get to that in a second. But let's think about this issue a little bit. Let's say you're working for a consulting firm that does some traffic data collection. I want to give you like maybe next 2-3 minutes to read through it and maybe talk to the person next to you. Is how you would approach this problem, and how would you start, and maybe you can come up with an estimate, maybe you can't, but let's kind of read through this problem for next 2 minutes, and then maybe talk to the person next to you and figure out what do you think would be the approach. And if you can actually come up with what estimate, that'll be great. And then I'll also be very interested in the assumptions that you might be making here. Okay, so let's read through this, and then let's take a few minutes to talk about this. Okay. Okay, so as you're thinking about this, what do you think is sort of missing from this mix of information? There is a lot of details here, but what do you think would you want to know before you can make an estimate? Yes, please. Yeah, so this is something interesting, right? So perhaps this will be, yeah, so what method you could use potentially. So here the assumption is that you probably cannot get automatically, right? Because if you could get the data automatically somehow through some sources, then you would probably do that, because that will be sort of the cheapest way to get the data. So let's assume that sort of the approach that you need to go is actually go out in the field, and you'll have some help of technology, like for example, those automated data collectors that I showed you. So you'll have some access to the technology. So you could collect the data real time. You don't have to necessarily record the intersection and bring it back to the office and then watch the recording or anything like that. So that's not what you're trying to do. So you can actually go out in the field and collect data using some help of technology. Okay, so that's one thing. So there's no, so that's where I'll start. Like that's one of the assumptions that you can make, that you do actually have to go out in the field and get the data. Anything else that you would want to know about the intersection? Yeah.
I guess a rough traffic volumes that pass through there, like
Yeah.
1,000 ADT or 15,000?
Yeah. So that's a good point, right? So would you want to know at the time what your what the scale of the problem that you're dealing with? Yes, you would want to know that, because that'll tell you how many people you might need, right? Because if there is the traffic volume at this intersection is sparse, right? Then you could maybe work with like maybe 1%, maybe even 2%. But if you're dealing with then, pretty heavily utilized intersection, like something like Foothill and Santa Rosa, for example, then you might not be able to get, with just one person, right? So you might need more people to actually collect the data and accurately collect that data, because there are so many movements to track, and every movement is having certain, but what makes, sort of limits your job, or at least limits the complexity of the job on a signalized intersection especially, is that not all movements will be moving together, right? Because you'll have, a certain number of movements, sort of conflicting movements won't be moving together if it's a signalized intersection. So that sort of limits the complexity of your task a little bit. But again, knowing the fact that whether it's signalized or unsignalized, and what is the level of traffic volumes that we're dealing with, would be useful. So let me sort of give you an idea, because all of us are sort of familiar with that. So let's stick with an intersection like Santa Rosa and Foothill, for example, right? So now you have a little bit more detail about what location we're talking about. What else would you want to know about that location? What does it not mention here? Anybody else want to take a crack at that? Yes, please.
I guess like location, like what popular spot, like next to it, like to the highway, that kind of stuff to help narrow down the peak hours. Like if there's a really popular spot, that's like first 55.
Yeah. I think those are, again, great points. Like sort of knowing the context, and then this is where sort of Google Maps and all these technologies can help you in, like, maybe you can ascertain what the land use around it looks like, and then that can give you some idea about traffic and what's happening there. Now, the other thing I would say is that you would want to know probably, go ahead, please. Yeah, bike lanes, pedestrians. What's the count? I don't think there's any mention of anything related to pedestrians and bicyclists here either. They don't say, but obviously, if you're tracking truck movements, you might want to track pedestrians and bicycle movements as well, right? Because, and again, you want to know approximately what that number looks like, because again, that could add the complexity to your job, and you would absolutely want to have some idea about would we have to track pedestrians, bicyclists, and to what extent those numbers exist at that location. So again, great point. Pretty useful information to have. What else? Anything else? Yes.
I guess since signal was mentioned, probably signal controls in terms of getting a better idea of how many people you need. Like if it's a permissive, like if it's a protected left, permissive left, is there a right turn on red restriction?
Right.
If there isn't, then you probably need more people, because you have to pay attention to the other sides.
Yeah, that makes sense. And then to answer those questions, I'm just going to say, let's kind of think about a picture in your head, an intersection that looks like Foothill and Santa Rosa, similar traffic, and the bike ped volume there can get pretty heavy as well. So let's take, like, maybe talk to your neighbor next to you, and like let's spend like maybe 5 minutes trying to estimate what that looks like. Okay, what that information looks like. And hopefully you get to do some of this stuff tomorrow in the lab too. So maybe it could be a group of 3 as well. So it's fine. Like if you're 2 or 3, I'm fine either way. Of person hours that you will need to conduct this study. Let's hear some estimates at the maybe in the range of like maybe 50, 100 person hours. Anybody in that high range? Right. So tell me what is the estimate? If you are closer to 50, what's your estimate? Like, what did you come up with? Yes, please. Yeah. 6 to 8 hours total, or 6 to 8 person hours per person. Yeah. And yeah. Yeah, and then there are 2 lanes on each direction too. So those 2, I think, and then but the good news is that at least some of those movements happen together. So I mean, it's not good news; it's bad news almost. Mm-hmm. So 8. So you said 8 hours, and then you're looking at 4 people. 7 to 8 people you'll need at the intersection. So about like maybe 60 hours. So 8 hour, you'll have to collect the data for 8 hours, and then 1 hour of travel time, like if you give or take half an hour, and then obviously everybody has to travel. So there is that. So you'll have to account for that. Okay. So anybody who got sort of the opposite end of that, like sort of lower end, like somebody who thinks that this estimate is pretty too much or too little, or what is that? Yes.
We did 24 hours using a 4-person team, and
So 24 times 4 or 4 times 6?
3. Oh yeah, we said no, 3 people. 3 people, and we're staying on 2 days, Wednesday and Friday, and we're studying 3-hour assignments from 3 p.m. to 6 p.m. Wednesday, since that's a typical weekday commuter, and Friday to see how the weekday commuter competes with the leisure commuter.
I mean, maybe you need Thursday night too, right, for the farmers market, or if you're talking about that intersection. But no, I think that's a reasonable approach, that you might have to make more than one trip, if you're gonna do that. So kind of accounting for those kind of things is useful as well. So yeah, that's good. So but you still came up with fairly low estimate to my, right? So or did you come up with, I think theirs was 8 persons, 8 hours for 1 day of data collection.
We did 3.
Well, I mean, we ask, and it's going to be the PM hours.
Yeah, looking at PM hours. So okay, so yeah, if you're not doing the AM morning and peak, so yeah, let's look at. So yeah, that will be sort of useful to kind of figure out, like, what's your assumption if you're just doing PM peak hour? Yes. That's okay. Yeah, I mean that's so let's kind of make it. So what you were saying, like 7 to 8, you can make it 2 to 3 rather than 7 to 8. Okay. So and then 3, and you said 8 people, so about 16 for 1 day of data collection, and then maybe if you want to do it for multiple days. So 16, yeah, 16 seems like a reasonable effort. Plus you added some travel time in there. Anybody came up with other things that we might have missed, or would that be reasonable? Yes.
Well, I was thinking like
We typically don't count that separately. We have sort of the technology available where we can, and I don't know if I showed you in that picture, but sometimes there is sort of a separate button to press to track like trucks. So there will be like, okay, when you're doing, and a lot of times you do it on the computer, or there are apps on the phone as well nowadays that are available where you're sort of tracking just the movement, but then if it's a truck that's moving, you press a sort of a different button on the screen or on the dashboard, and then that's how you sort of collect the truck data. So hopefully you won't have to have another whole person to kind collect the truck data by itself. So yeah, but that's, if you don't have that technology, obviously that'll be even more time consuming, right? So yeah, that's good. And anything else, anybody else who came up with some other estimate, other things that you might, that we are not accounting for? So you said three people can measure the data at that intersection?
So like.
Right. Yeah, the three, I think maybe you'll probably need just sort of one more person, at least one more person, partly because there are like sort of a lot of movements that go together on that intersection. And if I'm recalling correctly, there is even some, and then that's where your point about the signal timing is fairly valid and fairly good, is that, if you think about, you have movements like left and through, right? So that could be, sometimes they go together, but then there could be lead or lag phasing where, and we'll talk about phasing in the next module, but the idea is that, if there is sometimes left turn and the through movement is going together versus when the two lefts are going together, that could happen sort of simultaneously and sort of tracking that. So I'm thinking like, a 4-person crew would probably be needed. And if you have some technology available to you to measure the truck, I think maybe a 4-person crew is what you'll need. And depending upon how much data you collect, maybe 3 hours. So 4 times 3 is 12 hours, 12 person hours to collect the data. And then travel time for those people going back and forth should probably be a reasonable number. And then maybe one of those people will probably be a little bit more experienced in collecting the data so that, maybe, hopefully that won't be sort of a complete novice who hasn't collected the data in the field for a long time, or like me for a long time. In your case, probably never. But yeah, so you probably want somebody who's a little bit more experienced in sort of going out to the field, be familiar with field conditions a little bit. Just go ahead, man. Yeah, so I think if a 4-person team on that one, I would probably have like everybody at each corner and just sort of track the movements that goes with them. Now, that would get pretty sort of dicey especially if I have sort of, if I have left turn and through going together, that would be problematic. So then I'll have to kind of think about, okay, maybe the person who's standing at one corner is going to track, the through with the opposing left. And then hopefully they won't ever go at the same time, right? Through and the opposing left and that large of an intersection will never go together. So maybe that would be the for each corner, that's what you will track. So I'll probably put, and then when you're sort of, when you have sort of on those, when you have the gap, then you watch the non-conflict, or when you watch the non-conflicting pedestrian movements that are moving as well, right? And the good news about pedestrian movement is that because they tend to take a lot of time, as long as you assign who's measuring which pedestrians, hopefully you'll be able to capture all of them. And same thing with the bicyclist as well, because they do tend to take a lot of time when they're moving through an intersection. So that'll be something to kind of, so that's how I would track it. But again, as I was saying, like I personally haven't collected the data in a long time going out in the field. I've done some data collection on a video, but again, in video, you have the luxury of sort of being able to kind of go back and forth on certain things. And then there is a lot of technology with automated video collection as well. But I would say that, probably 4 people should be sufficient. Yes, go ahead.
In like this case, would we be able to reduce the amount of man hours if we simply just mounted a video camera and then came back and collected the footage and just analyzed that in the office?
Yeah, you could potentially do it like faster. And I think there might even be some, as I said, I was saying like, there might be some sort of technology there that now is available that you could actually use those video data. Now, good news for us is that at that intersection, there is actually video available. They don't use it to enforce or anything, red light running or anything like that, but they do have the video data available these days. So that's how actually, I think a lot of time these data are collected is that, you make that footage available on like, using a sort of a automated tracking of some kind. So there is like trajectory tracking video analysis capability software that are available now, and those can count the things for you. But again, on those ones, you just want to be careful about if those numbers are making sense. I mean, if they're broadly making sense, you're probably okay. And again, how would you know if they're not making sense? So you need to have some idea about what actually is happening on those videos. So some random checking that video at that each approach is sort of working correctly. So maybe sort of have the video output for 5 minutes and make sure that those 5 minutes outputs line up so that you could count on that data for the full hours or full 2 hours or whatever you're having that video analysis do the analysis for you, or that software do the analysis for you. You can rely on that. So always have some. So if you do have some, so yeah, you could minimize the time, but in that scenario, I would still budget some time for manually checking the data for at least 5 to 10 minutes, 15 minutes, even intervals, so that I know for sure that I'm getting good data. Okay, so that's just a little fun exercise to kind of think about how we can track movement. And I think you guys are going out to the field tomorrow, right? So that's the plan in the lab. So hopefully you get some experience of the chaos that happens on the street when the rubber meets the road a little bit. So that should be fun. Okay. So reporting traffic volumes, daily volumes, ADT, average daily traffic, average annual daily traffic. So in annual daily traffic, we always sort of collecting the data 365 days a year. So we're always continuously collecting the data and making our estimate. With average daily traffic, we're just collecting data partially. So maybe going out in the field for 3 days, maybe 10 days, 7 days, whatever it is, but just less than a year. Typically way shorter time than that. So a lot of times the data will be collected only for like 3-4 days in the year. And then based on that, we'll be making estimate for the average. And then hourly volumes commonly used for intersection. So we'll have hourly volume, equivalent hourly volume, and then 15-minute volume. And then, so this is the peak 15-minute volume, right? And then I should have said equivalent hourly rate. So how we get that is basically using the peak 15-minute volume and multiplying that by 4. So you'll get the peak hourly flow rate. So that's basically what that is. So hourly volume. So intersection, we're very interested in hourly volumes because a lot of time their level of service is pretty dependent on that. But even on roadway segments, we do rely on hourly volumes quite a bit because again, if you're doing the level of service analysis, we use the DDHV, which is the daily directional hourly volume, right? So that's what we try to derive. I'll give you a formula for that in a second here. As I was saying, AADT for 24-hour traffic for any period less than a year, and typically that is way less than a year. So we're looking at, like, as I said, maybe 3 days, 5 days, 7 days period. So pretty short amount of period. But then AADT is when you're actually collecting data in the field for the whole year. So ADT is, you can think of ADT as sort of an estimate or a guesstimate of AADT. And then one thing to note here is that the 365-day count is rarely done. Like, we unless we are doing some kind of automated data collection where we are, where we have loop detectors in place, right? So in those streets, yes, the AADT is available, but in most places, 1 to 2 days of count annually or biannually, and then we just sort of convert that. And ADT may be converted to AADT using adjustment factors. So for example, if you collected the data on a Sunday of January, right? So you need to multiply that by 1.58 to get AADT, right? Because you assume that, way fewer people will be traveling in January. Now, if it's a nice weather town like San Luis, maybe those factors would change. So I think these are I think from the state of Michigan. These are like, state DOT published database. But I just, these numbers by themselves don't mean anything except for the fact that, you should be aware of what these numbers are coming from, right? So they're coming from the fact that, total amount of travel in a sort of a state that experiences pretty cold weather versus to a reasonable weather. So you could see that, if you go into the August month, the adjustment factor on a Friday of August, the adjustment factor could be as low as 0.76. So you could see that if you go out in the field and collect the data on a Friday of an August, right? An August Friday would have way more traffic in the field. So if you are making projection for the whole year based on that data, you multiply by a factor that's way less than 1, right? But if you go out on a Sunday in January, you're going to see way fewer people on the road, right? And that means you need to apply a pretty heavy adjustment factor to get to the average annual daily traffic if you want to convert on the basis of that data. So you have to project a pretty high number. So that's all you need to sort of worry about. But again, if you go on a weekday, the numbers reduces quite a bit because obviously if people have to go to work, they have to go to work. You know, if it's January, February, it doesn't really matter all that much, right? But then in the summer months, there might be some additional sort of traveling public who might be visiting the area during summer vacation or whatever comes in as well. So that factor goes down quite a bit. Okay. So something to kind of keep aware that you could convert AADT, and then you could find these published factors for the areas that you're interested in for your location. You know, typically state DOTs will publish that for you. This is just coming from Michigan. And then, so this is sort of the formula that we use. AADT could be adjusted by 24IJ, 24-hour volume for day I in month J in vehicles. And then DFI is daily adjustment factor. MFJ is the monthly adjustment factor. And then this is the combined adjustment factor for month and the day of the year. So if you apply both of those factors, you could get your AADT. An estimate, that'll be an estimate, but you know, it'll be fairly reasonable estimate for you to use. Again, this is state highway system, daily factor, and monthly factor. And then, you know, you can multiply both of those and you could see that these factors sort of change. So if you multiply, so for example, 0.789 on a Sunday, so daily factor is pretty low here because obviously you're gonna, so for a contiguous area on a state highway system, these are the factors you could use, and then you could multiply that. So whatever volume you observe, you can multiply these factors to those and be able to get that. And this is coming from an old textbook that I used to use for this class. And you can find these tables for your area. Again, you know, specific factors are not as critical as kind of knowing what these factors ought to look like for a reason and what's the reason, do they make sense or not? So anytime you're sort of looking at these numbers, they should always make sense and be aware of that. And typically the DOTs will publish these types of numbers if you need it. Okay, so this is sort of your homework problem: peak hour, directional design, hourly volume, and this is your K factor and D factor. How many of you've heard of these K factor and D factors before? Has anybody? Where did you hear it? 321?
Yeah.
See, 321. Yeah, that's where we talk about these a lot. But the idea is that K factor is what proportion of daily traffic occurs during peak hour. D factor is proportion of peak hour traffic traveling in the peak flow direction. Okay, so you could, so this peak hour K factor and D factor, you know, they vary based on what type of area you're talking about, right? So in rural areas and urban areas, these things do differ quite a bit. So for example, if you're talking about a rural area, so in urban areas, traffic is usually high, regardless of the time of day. So your K factor is normally a little bit lower. So you could see that in urban areas, and so for a couple of things to note here, in urban areas, let me point out here that the K factor is anywhere between 0.07 to 0.12. That means if you take your daily traffic, right? And we know that daily traffic is not uniformly distributed over the whole day, right? We know that. So you can assume that about 7% of the traffic, between 7 and 12% of the traffic happens during the peak hour. About anywhere between 7 to 12%, right? But in rural areas, that number is about 15 to 25%. So in some rural cases, the peak hour traffic could account for almost 25% of the traffic. That's a pretty insane number if you think about it, right? I mean, 25%, 1/4 of the whole traffic is for 24 hours of the day is happening within 1 hour. I mean, it's completely flipped picture, right? I mean, you would think, I mean, obviously we never have uniform distribution of traffic, but if there were uniform distribution of traffic, you will expect like, about 4 to 5% of traffic to occur every hour. But here you can see as high as 25% of traffic occurring during one peak hour. So that's a pretty sort of could be pretty problematic from a distribution of resources standpoint if 25% of your traffic is happening in 1 hour, right? Yeah.
So this more or less affects the signal phasing you use, so you have run like peak hour or commuter hour phase and the standard phase.
Right. So basically, what you'll run in that case is, so that's why it's very, very important for you to have actuated signal in the rural areas, right? So in urban areas, you can pretty much get away with pre-timed signals because, again, the traffic might remain high, and then you could sort of switch to even like a flashing yellow or something during nighttime in urban areas. But in rural areas, you pretty much always need some kind of actuation so that you're serving the demand where it exists. So the question was like, how does that affect our phasing? That affects our phasing because the actuated signal becomes so important in rural areas because the demand could be pretty significant and could only occur from one direction. And then that's another thing, right? On the other side, look at the D factor too. In urban areas, D factor is something like 55 to 60%. So that means the peak hour is accounting for, or peak direction is accounting for 55% of the traffic. And then the non-peak direction is 45%, right? So maybe, obviously that's not equal, but it's pretty close, right? It's pretty close, 55, 45, and then maybe the AM direction is switched over. But look at this. In rural areas, that could be as high as 80%. That's again, pretty significant chunk of traffic is happening during peak hours. And that creates a lot of problems sometimes, right? Because you're allocating resources for 1 hour when you're sort of, but then the rest of the time, the traffic would not be, basically there will be an empty road attached to it. So it's pretty interesting, but then, and that's why, if you have routes like this where the D factor is 80%, right? Maybe there is something, and then the K factor is also pretty large and D factor is pretty large. Maybe there is opportunities for you to kind of think about what other, traffic control strategies you could adopt. And when the time comes, we'll talk about those. But there might be some, I think I mentioned the edge lane roads the other day, and they become sort of maybe an interesting choice for you to think about in those types of characteristics where D factor is so high that everybody's sort of moving in one direction during morning peak hours, and then the afternoon peak hour, everybody is moving in the same direction on the other side. There's not a lot of oncoming traffic coming along. So could be interesting choices there. But this is sort of the crux of all problems here for us, right? Like, we have distribution of traffic that's very concentrated during peak hours. So we have to satisfy that demand. But then the rest of the time, our investment sort of sits empty. Nobody uses it. And it takes just to kind of satisfy that peak hour demand. We have to spend so much money. And that's a problem. And then this idea of this radial route and circumferential route, it's basically, if you have a central city, CBD, central business district, where everybody is coming to, and then circumference would be like, the routes that connect, major sort of arterials, right? So, so I hope you know what that means. So maybe I should sort of quickly draw it out. So if you kind of think about, so you're, you have a city, and then you have sort of like CBD in the middle. And then there could be radial route that sort of disconnect different neighborhoods to that, right? And then you might have some routes that connect these routes themselves. So these will be sort of your circumferential routes, and then these will be your radial routes, right? So you have to kind of think about whether it's a radial route or not. Radial route will typically have, because they're connecting outlying area with the CBD, so the central business district, they typically have a higher D factor, as you could see here, right? So radial routes will have a D factor to be a little bit higher, and there is pretty much no other difference between the. So in urban areas where you have some central business district, you have the radial routes to have a little bit higher D factor, and then same thing with the rural routes as well, right? So you have these higher D factors that come into play on radial routes because they are sort of serving that peak demand to that central business district. And it doesn't have to be central business. It could be a place like Cal Poly, for example, where there's a lot of demand. And then you would expect, for example, on California, right, the D factor would be pretty large, right? Yeah, and you've seen that probably going in and out of the campus in the morning and afternoon peak hours. Okay, so let's see clear. So this is sort of the Caltrans data. So Caltrans provides these data, and in our 529 class, we make use of these sheets quite a bit, right? So these are sort of traffic volume sheets that Caltrans provides for all state routes in the state. So all state maintained routes have this sheet available on Caltrans's website, and I provided the link earlier to you. And you could see that they provide the K factor, the D factors, and all of that here. And here you can start to sense a pattern, right? So if you can see the county, the LA County, for example, has, but if you kind of go away from the city of LA, mile marker, sort of the outlying areas of the LA County, then the K factor becomes a little bit larger. And then the D factor is pretty similar. And then Ventura County, and then if it's a rural area, it says R here, and that's sort of, I think that's what that is. And then you could see that they provide the volumes, they provide when the peak hour happens. I don't know if they provide when the peak hour happens. Yeah, so this is the direction of the peak hour. And then this is the K and D factor combined. So you can multiply that between so this is just 3.98 is just 7.44 times 53.47 divided by 10 raised to power 4, because these are all percentages. And then when was this data collected? Saturday in July. So you can see that some of these areas could have peak hour on state routes. That's like not in workday or anything like that. It's basically serving the traffic that comes out of LA and wants to go to Santa Barbara for a weekend or something, right? So these things could happen on different times of day and all of that. And this is like happening at 12 hours. So this is sort of your afternoon peak hour. And then, or not afternoon, sort of midday. It's happening during midday here.
Highway 1.
It's Highway 1. So it's basically you're serving a lot of tourist traffic as well. So
I was looking at the one that we did
where is the midnight here?
For Santa Barbara Highway 1 Sunday, May has a D of 90.78.
Oh, so that's basically 90.7 right here, right?
That's midnight.
So 90.78. Yeah, so this is sort of, so this is probably they were looking at some event that happened, or maybe something was let out at that time. Sunday in May, maybe something related to Memorial Day, maybe possibly. I don't think they say that here, but yeah, so this is kind of insane, right? So happening right at 11 to 59 to 12:59. That's pretty intense there. 90%, and then obviously 6% of the traffic is happening of the day. So not a large number, but again, 90% traffic going in same direction is interesting. And so this is the mile marker here. I'm not sure what the CS stands for. And then this ahead and behind is basically in the context of the nearest ramp where the data was collected. So that's what that is about. Yeah. And then the direction is there. And you can get a good sense of one-way peak hour volume. What is that? And typically you will know that the AADT or ADT value, that's measured in both directions. Okay, so anytime you're given an ADT or AADT, you know that this is on both directions of the roadway. And then when you multiply it by K and D factors, that's when you get the design directional volume. Okay, so that's what's happening there. And then is there anything I want to talk about? So yeah, this is AM peak, this is PM peak. So always look for that depending upon the analysis you're running. you want to look at the correct number there. What else? And then just knowing when the peak hour is happening. So PM peak hour is happening at sort of 4 p.m. But yeah, this is midnight. Kind of weird. I would, I would probably check the data one more time if I see something weird like that. What was going on? Maybe there was some malfunction that's probably not reporting the data or something. So I would want to be careful about, sort of. It's possible that could be a midnight thing, Sunday midnight, so something like that's happening Saturday night, some event or whatever, and that's possible. But again, if I see something pretty unusual like that, I'll go back and check the data one more time as to what was actually going on there. So, so something to think about there. Okay. So sometimes volumes are only collected for a portion of the hour. Maybe there was a problem. Maybe you couldn't stay for the whole time. So you can convert the volume into equivalent hourly volume. So if you connect for 15 minutes, then you multiply that by 4. So 300 vehicles counted in 23 minutes. That equivalent hourly volume will be 782 vehicles per hour, right? So you could always do that. So if you count for 15 minutes, you can multiply that by 4 and so forth. Okay, so yeah, so this is sort of so we're talking urban arterial. What range of design directional volume? So I'm asking you range, right? So how would you go about approaching this problem? You got AADT of 50,000 vehicles per day. So I'm just going to go ahead and write this down. So you got an AADT of 50,000. So directional design hourly volumes would be expected. It's an urban arterial. So what would you do is basically go back and see. So this is your AADT and you want to derive the DDHV, right? Design. DDHV is question mark, and what you're given is you're given the AADT and you're trying to find the DDHV. How do you go about doing that, right? So it should be pretty straightforward. And I'm asking you for a range, right? That's where you'll come out. So I'm looking for range. So range implies that I'm looking for maybe the minimum value of DDHV and the maximum value of DDHV, right? So what would that look like? Which numbers would you use from here? I mean, here you'll have to make an assumption whether it's a radial route or a circumferential route, right? So if you make an assumption it's a radial route, then there will be not one range that you will get. But if it's a circumferential route, then you'll get another range, right? So what's the highest possible DDHV that you will get? How would you get that? Based on this number right here and looking at these numbers. So let's see if we can maybe take a minute to sort of estimate that. The range. Yes, please. Yeah, it's urban. Urban is mentioned in the problem, actually. So I don't have that problem pulled up here. But if you go back to that slide, urban is in fact mentioned in the problem. So to get the minimum value of that range, what K factor would you want to use? 0.07, right? What D factor would you want to use? So again, I don't think I'll combine whether it's a radial or circumferential route. So I won't combine that into a range. I'll probably make an assumption because that doesn't make sense to me. It's kind of providing a range for both radial and circumferential that combines the two. No, I would probably make an assumption that, okay, and either assumption is fine in this case, right? I could say, okay, so first thing I would do is like, okay, I'm going to assume it's a radial route, or I'm going to assume it's a circumferential route. And once I've made that assumption, then I'm going to start working on my range. Okay, that's kind of seems reasonable to me. I won't want to make an assumption or start saying that, okay, 0.07 to 0.50 is going to be my range. No, I think I would want to make an assumption about radial or circumferential, one of the two, and then provide my range based on that. And maybe I can report two answers. If it's a radial route, this is my range. And if it's a circumferential route, this is my range. Okay. I wouldn't want to combine the two and come up with a range from this to that, that kind of mixes the two up. That makes sense what I'm trying to say here, right? So just make one assumption in these types of scenarios, because you could potentially make those types of assumptions a lot. So yeah, so 0.07, and let's say if you made a radial assumption, what's going to give you minimum value of DDHV, assuming D is 0.55, right? So that's how I'll approach it. K equal to, so I'll say assume radial. Right? If I assume radial, K will be K min is 0.07, right? And then my D min is, and obviously it's an urban area given to me already, so my D min is 0.55, right? So I'll basically get the lower end of the range by multiplying 50,000 times 0.07 times 0.55. Does anybody have the number for me? Please give me a number, shout it out. How much? 12,925? 1,925. Right? Give or take, right? Yeah, so you'll get that number. And then on the upper end of things, you'll get basically these same calculations, but with 0.12 as my higher range, and then 0.60 as my sort of upper end on the D factor. And then that will give me how much? 3,600? Okay. Or 2,600? 3,600, right? Yeah, that's right. So here is the problem, right? That's a pretty big range, right? So what's your conclusion now? So you need to actually have a pretty good idea about what you're dealing with here to be able to convert AADT into a design directional hourly volume. You can't rely on these ranges, because these ranges will take you, 1925 to 3,600. That's one heck of a range, right? It's a pretty big range, and your sort of solutions that you want to provide would vary quite a bit based on what you're dealing with here. So that's why, obviously knowing what the range is and what so suddenly if you start seeing in an urban area D factor equivalent to 80%, then you want to get concerned, right? You want to at least evaluate those specific circumstances. But even knowing, that might not be sufficient. You obviously want to investigate what's going on in your particular area. So having a good sense of K factors and D factors for your area is pretty important. So that gets us back to the importance of being able to collect good data. Okay. So talk about this. Yeah, suburban segment of eastbound I-80. Again, you can, I'm trying to estimate the DDHV, eastbound I-80, suburban segment. Eastbound I-80, I want to, AMP car, again, you'll have to estimate the D and K and D factors, and then kind of go from there, right? So I'll let you guys work on that a little bit. And then peak hour factor. So this is sort of peak 15-minute volumes, relationship between hourly volume and the maximum rate of flow within peak hour. So PHF is the peak hour factor. It's equal to hourly volume divided by the max rate of flow. So capital V that you're going to assume. And again, one thing to remember is maximum rate of flow. So anytime you mention rate of flow, it's measured per hour. Okay, I think I mentioned that before, but I'll reiterate that here. Is that so? And sometimes on freeways, we might actually consider the same idea, but with 5-minute volume. So on intersections, most of the time, we'll take 15-minute volume and multiply that by 4. But sometimes on freeways, we might get every 5-minute data and then multiply that by 12 to get a good sense of peak hour factor. Okay. So we take the worst 5-minute volume and then multiply that by 12, because we are converting that into flow. So this formula becomes 4 times V or 12 times V5. So for freeways, So for freeways, the formula will become V, capital V, the hourly volume divided by 12 times V5. Okay, so 12 times V5. So 5-minute volume and multiply that by 12. Okay, on freeways, sometimes we'll consider that to be our sort of formula. Again, the bottom line, the denominator on this is called peak 5-minute rate of flow. Okay, so now this will be called, so denominator, this denominator right here is peak 5-minute flow. Okay. So always remember that denominator in this case is always going to be rate of flow. So always convert it into hourly rate, right? Equivalent hourly rate. Okay, let's see. Okay. So this is an example problem of estimating peak hour volume from here. Okay, so let's see, if you're given these data points, peak hour volume, what's your peak hour volume? You know, you can add those up and get your peak hour volume. Right? What's your peak hour volume? Anybody has the number? Oops. PHV by adding those up. Oops, let me. PHV equal to, what is that? What's the number? 1989. Huh. Taylor Swift album. 19. Oh, if you didn't know about me, I'm a bit of a Swiftie, right? You know that, right? Okay. All right. You should probably know that. I couldn't quite afford the tickets to go to the concert, but I'm going to watch the movie. So that's the level of Swiftie I am. Okay. PHV, 1989. Okay. And then let's get the peak hour factor if I want to derive the. So what is the peak 15-minute rate of flow? What is the peak 15-minute rate of flow? How would you get it? It's 4 times 604, right? And that will be 2416, okay? 2416. So that will be, again, VPH, vehicles per hour. And then if you want to derive the peak hour factor, that's 1989 divided by 2416. Okay, so you can get the peak hour factor. Now, if you're given longer data as you are in the homework problem, right? You have to do a rolling addition and find the 4 consecutive 15-minute periods that give you highest number. And then you keep doing it and then find the peak hour. And then from that peak hour, select the worst 15 minutes and then derive the value. So there is a homework problem on this that you should be able to solve as well. Okay, so I'm going to stop here and I'll see you guys on Thursday. Have fun in the lab tomorrow. And I'll see you guys on Thursday or in my office hours.